So this is the DC average of an alternation, right? Are y'all okay there? And like I said, the actual true formula is 2V peak over pi. And then how do they come up with 0.637? Is they pull V peak out in 2 over pi, and this is where the 0.637 came. But to me, it's just a lot easier to remember V peak over pi, 2V peak over pi. And of course, this is peak right here, and what we do is do the positive peak. What's the average DC value of a sine wave, of a cycle? What is the average DC value of a cycle? What is the average DC value of a cycle? Zero. The average DC value of a cycle is zero. And how did I demonstrate this to you? I put my meter in my wall outlet and put it on DC, and what did it measure? Measures zero. Right? You understand? And why is it zero? Because so if I took a positive 0.637, added it to a negative 0.637, and took the average of that, it would come up and give me what? Zero. So what did they do to figure out what they call the effective? We don't call it. It shouldn't be called. Some people do that by mistake because it is similar to an average. But what do we call the effective voltage of AC? Anybody remember? Yeah, it's got a name. Huh? RMS. So when we give voltages, like we say, Alabama Power, we have 120 volts at our house. If they don't specify RMS, it is RMS. So we take for granted AC voltages are given in RMS. Y'all understand that? And if it's not RMS, then we specify V peak or V peak. So we give AC values three different ways. We give them as RMS, and we give them as peak, V peak, or we give them as V peak. That's the way we give AC values. We don't use average, we use what we call effective. Now what we mean by effective, if I have 120 volts AC applied across a 1K ohm resistor, or if I have 120 volts DC applied across a 1000 ohm resistor, you get exactly the same effect. You get the same power. So that's why it's referred to as the effective voltage. Even though it takes a lot of peak-to-peak voltage, why do we calculate 370 volts peak-to-peak to get 120 volts RMS? Huh? It takes 370 volts peak-to-peak to get 120 volts RMS. It's actually 369 point something, 0.7, I think. Now this waveform is called a sine wave. And how did it get that name? Nobody knows? And y'all, most of them had AC. How did you get the name? Most of you know how you got your name, right? Except some people, they don't name it out of their, most in the old days when they came up with children's names, they was named after somebody else in the family. But that's not quite true anymore. But But you know how you got your name. I mean, usually even if they give you a strange name that they got off the internet somewhere, they will explain, well, Mom, how did I get my name? And they'll tell you how they came up with your name, right? So sine wave, that's a strange, that y'all remember that. Y'all named y'all's first kid that, right? Come here, sine wave. So my son's got a friend. He's an avid sportsman, and he named his first son Hunter, and his second son he named Fisher, Hunter and Fisher. So how did the sine wave get its name? Well, when we generate a sine wave is generated on a circle, and a circle is equal to how many degrees? How many degrees? 360 degrees. So what we've done is we've adopted that over to the sine wave, but we don't call it rotational degrees, we call it electrical degrees. So one cycle would occur every 360 degrees. So this would be 0 degrees, this would be 90 degrees, this would be 180 electrical degrees, this would be 270 electrical degrees, and this would be 0 degrees, but it would be, this would be 360 degrees, but it would be 0 of the next cycle, right? You understand that? 270. Right? I understand. And of course, 30 would be right here. 45 would be up in here. Well, what we can do is that if we put this on the circle, how it's generated, then we come over here, this forms a special triangle called a what? Right triangle. Okay, you understand that? And if I know the length of this, side, which we call the hypotenuse, I can calculate the length of this side by taking the trigonometric sine of that angle. So on your calculator, if you got a scientific calculator, which y'all supposed to have, and I keep mine right here. Oops. So here's sine. Sorry. Here they are. Don't look at the H's. Here's sine, cosine, and tangent. So the radius of the circle is equal to VP. Y'all understand that? So that means if my VP value was equal to, what do you want it to be? Huh? 90? We can make it even. 90 volts, but we're talking about volts. Okay. Then what would be this voltage right here at 45 degrees? Now most people think it's half, but it would be half if the waveform looked like this, right? You understand? And the waveform don't look like it. It's a non-linear waveform. So what would that be? Well, I could come over here and take VP. I can take the peak value, which was 90 volts. Okay, y'all understand that? And then I'll multiply that by the sine of 45 degrees. And then I would come up here and get equals. So that would be the voltage at 45 degrees, 63.6. What should it be at 90 degrees? Well, at 90 degrees, it should be 90 volts, right? You understand that? So let's see. So I'm going to say 90, and then I'm going to say times 90 sine. Well, look what the sine of 90 is. It's 1. So at 90 degrees, it would be 90 volts. Well, what would it be at 270? Well, at 270, it should be minus 90, right? You understand? So let's see. So I'm going to say 90 times, right, 270 sine. Look what the sine is. It's a minus 1. I hit equals, and it says it's going to be a minus 90 degrees. So what we're saying, and what would it be at 30 degrees? Well, 30 degrees is going to be exactly 1/2. So I should expect 45 degrees. So 90, as soon as I do it right, 90, right? And then times 30, look what sine is, 0.5, equals 45 volts. So what we're saying is the voltage of a sine wave varies with the sine of the angle. So since the voltage and the current and the power, all of them vary the same because, you know, power and current and voltage are basically proportional to each other, right? You understand that? Then that means they all vary with the sine of the angle. So since all these values vary with the sine of the angle, what do they call this thing? What's it called? It's called a sine wave. It's actually two words. I write it as one, but most people get that. And this is what this explains right here. But this is something we don't need to know, but that's what you learn in AC, you know, but all we're doing is seeing why is it called a sine wave? Why do we have to use RMS and why can't we use an average? Because if I used an average of the positive and the negative peaks, it would always come up and give me 0. Because every positive value has a what? Has a negative value that cancels out. So we came up with a method called root mean square. So RMS stands for what? Now mean is another word we use for the average. And then square. That's what it stands for, but what does it mean? It means we take the square root of a large number of equally spaced measurements on both the negative and positive. So that means for every one we have down here, we would have the same one on this side right here, right? Of equally spaced, I don't know what to say. We'll say voltages. Then we do what? Then we take the average, which would be the what? The mean, right? I'm sorry, I got this backwards. That's right. We take the square root of I got it backwards, guys. We don't take the root of the means of the squares. So what we do is we take the square root of a large number of measurements squared, right? Does that make sense? Of the measurement squared. So that means if this was a -1, if this was a +1 and this was a -1, what happens when you square a number, a negative number? What happens to the sign of the number? It turns in positive, right? Y'all understand that? If you square a negative number, it becomes positive. So what we're doing now, then we take the mean, and we're taking the mean of all nothing but positive numbers. But the mean is going to be a mean of the squares. So what do? We take the square root of the answer, and then that gives us the effective voltage. RMS works on any value, any AC signal that has both a negative and positive value, where the negative does not cancel out the positive. So we get as much work out of a negative AC voltage as we do a positive AC, right? You understand? Yes or no? Now, what did I tell you? On a sine wave, if it's a sine wave, then that value will always equal to 70.7%. So if it's a sine wave, then VRMS will always equal to V peak, and we use the positive peak, because AC has no sign, right? You understand? If you use the negative peak, you would come up and get a negative number, so we use the positive peak. The negative peak and the positive peak are exactly the same value, they're just mirror images of each other. Times 0.707. And this works great for sine waves. Alabama Power generates sine waves, right? You understand that? So it works great for power. It don't work great for AC waveforms that are not sine waves. So if you're in a field that deals with AC waveforms that are not sine waves, then what type of meter do you need to buy? This guy right here wouldn't work. It would read something, but it would be inaccurate. This meter right here uses 0.707, which works with sine wave. Right? What's the meter that you need to buy if you are looking at AC waveforms that are not sine waves? It's called a what type of meter? Huh? We talked about it the other class. Sometimes I think I'm just talking up here. It's called a true RMS meter. It costs a lot of money. You don't understand that. But if you're into variable speed AC drives and stuff like that, then that would be the meter you would buy. If you're dealing with just Alabama Power, then just these guys right here, they're a lot cheaper. So this is where so 0.707. How many of y'all can remember 0.707? 0.707. And now we got it. So that we got a lot of numbers, but if you remember 0.707, guys, you got it. Because let's say I'm going from VRMS to VP. I'm sorry. How about I go from VRMS to VP? So which is bigger, RMS or peak? Good. So I'm either going to multiply by 0.707 or I'm going to divide by 0.707. If we divide by a fraction, we come up with a bigger number. If I multiply by a fraction, I come up with a smaller number. So to go to V peak, I would take my VRMS and I would divide it by 0.707. Now what if I wanted to go to V peak? Peak to peak. You'll just say V peak times 2, right? And you'll look over here. This uses 1.414. It uses all kind of things. Later on, we'll see. Sometimes we would use 2.82. Sometimes we do all this kind of stuff. But all you got to do is 0.707. And you got to figure out, oh, do I need to multiply by 0.707 or divide by 0.707? Y'all understand that? If I'm going to V peak, then I'm going to divide by 0.707 because V peak is the largest. If I'm going to from V peak to RMS, I'm going to multiply by 0.707. If I'm going from V peak to RMS, I would take V peak to peak, divide it by 2, and then multiply it by 0.707. Now, why do we need to know that? Probably we have 2 pieces of test equipment that we use a lot. Now, the predominant piece of test equipment is your meter. But the problem with the meter is your meter does not show you what's there. It's either going to show you the effective voltage or it's going to show you the average voltage. Well, the problem is they don't troubleshoot stereo amplifiers, and that doesn't troubleshoot communication systems. What we want to do is we want a piece of equipment that shows us what's there with a picture instead of a reading. What's the saying? A picture is worth 1,000 words. So what we have a device called an oscilloscope. And what does the oscilloscope do for us? It lets you see what's there. Not measure what's there. We use it to measure, but it actually lets you see what's there. So this is the oscilloscope, and some of y'all's had AC, and you've used one of these things, and they're really neat. An analog one, about a 25 megahertz analog scope, which is real big, will probably cost you around $250. This is a digital scope. This is a 25 megahertz digital scope. This is around $500. Now, the advantage you get of a digital scope, of course, is number one is the size. They've got combination units out there, but are handheld. They're meters. You can use them as a meter, or you can use them as an oscilloscope. Those guys get up around the $1,800 range. But you have one piece of test equipment that you can use for two different things, right? You understand that? But what this does is it shows us what's actually there. So I can actually see that sine wave. And also, even troubleshooting power supplies, which is the first thing we're going to get into, you can't hardly troubleshoot a power supply without an oscilloscope. Sometimes you can, because there's certain things that happen, and by looking at the waveform, you can tell what component fails. Usually just by looking at the output of the power supply, you know what's failed inside the power supply right off the bat. So we have some analog scopes in there, but what you'll find out is once you learn how to use one oscilloscope, they're all basically the same. And we'll be using this semester. And it looks intimidating because it's got a bunch of knobs. But you got to realize this is like having 2 meters. An oscilloscope cannot measure current. An oscilloscope cannot measure voltage. Cannot measure resistance. An oscilloscope measures one thing. It measures voltage. But it measures that voltage relative to time. So time goes this way. So it's on the horizontal axis, and then voltage is on the vertical axis. But what does the oscilloscope measure? It does not measure RMS, it measures peak to peak. I understand that. So if I had the RMS value and I wanted to see how that would look on the oscilloscope, then I would have to convert from RMS to here. A lot of times we'll see we need to go from the scope over to a meter. Now the meter's going to read a lot less, right? You understand that? Yes or no? So Alabama Power, optimal voltage, or what National Electrical calls the nominal voltage, is 120 volts. Now, if I say 120 volts AC, what is that? If I don't tell you what it is, what is it? What? If I don't tell you what it is, what is it? We got 3 ways we can measure AC. We can measure it RMS, we can measure it V peak, or we can measure V peak. If I don't tell you what it is, what is it? RMS. So this is 120 volts RMS. What would this look like on my oscilloscope? My oscilloscope measures peak peak. So tell me, what would I do first? Huh? Find V peak. Okay, so I'd say V peak. What's V peak equal to? Are we going up or are we going down? Is peak greater than RMS or less than RMS? Huh? Greater. So are we going to divide by 0.707 or multiply by 0.707? We're going to divide. So I'd say 120 divided by 0.707. What does that give us? Hopefully I have your calculator. You can use your calculator on your cell phone. What's that? Yeah, 169.7 volts. Now I should put that out there. Now notice what I did a little different here. Up here I put V, down here I put VP. So I have to tell you or identify that as what type of voltage that is, right? Okay. So now I need to know my oscilloscope. I'm going to go voltage peak to peak. What would be my voltage peak to peak? Peak, not divide, peak to peak, right? Yeah, pi 2. So it basically says what it is. So that'd be 169.7 times 2. And what would that give me? You can't say 3 point. I can't take 169 and multiply it by 2 and get 3 points on it. Be careful, you might have yours in engineer notation, right? What's the engineer notation? So what we got? 339.9 volts, but look what I have to put now. I have to put, well, I put DPP out there, indicating that's what? 339.4. Usually we say 340. Well, no, we just 340, an even value is better. And what's the odds of it being 120 volts? Slim to none. The voltage can range 120 volts plus or minus 10%. So what you get to your house might not necessarily be 120 volts, right? You understand that? So normally we say about, I say about 340 volts peak to peak, and that's what my scope would measure. And we'll look at that later on to see how our scope would measure that much voltage. And it will. And we'll look at it. We'll look at Alabama Power. Let's say my scope is measuring 18 volts peak to peak. What would my meter measure? So what's the first thing I would do? I would find V peak, right? So what's the difference between V peak to peak and V peak? I divide it by 2, right? Because we're going peak to peak. We got 1 P, going from 2 P's to 1 P, right? What would that give me? Give me 9 volts peak. And then how would I go to volts RMS? I would take the 9 and I would multiply it by what? 0.707. So what would my meter measure? When we less than 9, 70.7%, or about 70. 6.4, and this big volts peak. Oh, I'm sorry. Thank you. We wouldn't put RMS up there. We just say volts. So in AC, if we give volts, that is what? RMS. And then we define whether it's peak or peak to peak. So an oscilloscope measures what? Peak to peak. Your meter measures RMS. An oscilloscope measures voltage peak to peak. A meter measures RMS, voltage RMS. Now we're talking about AC. And this is important, but the DC average of a cycle is 0. And this is why when you put your meter on DC and you look at an AC signal, it's going to measure 0. If it's a sine wave. If it's non-sinusoidal, which means if your positive is greater than your negative, then your meter will show you some positive value, but it's not going to be right? You understand? If it's a 0.707 meter. If it's a true RMS meter, It could be non-sinusoidal. Your negative could be bigger. Your positive could be bigger. Your negative could be distorted. Your positive could be distorted. It don't make any difference. A true RMS meter will measure the effective voltage. So that's the advantage of it. Now here at this school, a true RMS meter would not do you any good at all. Except showing somebody, hey, I got a true RMS meter. Yeah. And in most applications, it's not required. But if you get out there and you're working on like variable speed AC drives and stuff like that, those suckers generate non-sinusoidal signals. Or signals that are sine wave. Three phase. So what's our main power formulas? How do we calculate power? Very important. What's the three main formulas for power? These are formulas you should know. Power is very important. Power, we can't have power without voltage, and we can't have power without current. But basically, power is the most important. Why is power the most important? That's how much work you're doing. Right? You understand that? Well, I could have 1,000 volts, but if I don't have any watts, I don't have any watts. Don't have any work. So what's our main power formula? P is equal. This is one of those formulas you should know. You should not a formula sheet. By the way, on the formula sheet that I gave out, Ohm's law was not on that formula sheet, and Watt's law was not on that formula sheet. Because of any formulas you get out of here, these are the ones you should understand. Like I said, you might not ever use them, write them down, but if you got these in your head, you know what's going to happen. You have a feeling of what's going to happen when one of these things changes. So what's our main power formula? Yeah, V times I. Also could be labeled as E times I. Yeah, either one of those are legally fine. A lot of people like to use E because they don't want V on both sides of the equation. So you're solving for V, and then you put V on your answer, right? You understand? So another term for voltage is what they call an electromotive force, an EMF. So books use E. That way you solve for E, but your answer's got a V, right? You understand? Mathematicians don't like to have V on both sides of the equation. V equals 300 V, right? So them V's should cancel each other out. And then we have the derivatives of this. So we have power, and of course then we have Ohm's law. So Ohm's law, what's V equal to in Ohm's law? Yeah, I times R. So if V is equal to this, what does that mean I can do? That means I can substitute I times R in any equation. So it means I can say P is equal to I times R times I. Y'all understand that? Yes or no? So here's that I right here, and what did I do right there? I substituted what Ohm's law says V is equal to. So our second formula is P is equal to I squared R. Now, where did I squared times R come from? Well, it came from P is equal to V times I, right? You understand? Now, what is Ohm's law? What does Ohm say I is equal to? V over R. So that means I can come over here and say my power is equal to V, right, times V over R. So what I've done here is I've substituted what Ohm's law says that I is equal to. So that's our third formula. So power is equal to V squared over R. So we have three power formulas. We only have one Ohm's law, but we have three power formulas. But the main power formula is P is equal to V times I. And then how do they come up with the other two? They use Ohm's law to substitute for what Ohm's law says those values are equal. So what's our power formulas? Power is equal to V times I. Power is equal to I squared R. And then power is equal to V squared over R. Now this is single phase AC. So we have another way we transmit power, and it's called three-phase. And what we do is we use 3 conductors instead of 2. And we send 3 versions of the sine wave, and each one of them is separated by 120 electrical degrees. It requires 3 conductors, but if we use what they call a delta arrangement, we don't have to use a common. We don't have a ground. So this is why your main power feeds, you'll see combinations, you'll see 3 conductors, but a lot of times they'll use multiple conductors to send the power. We use it by 3-phase. Power distribution is 3-phase, all the way down to almost to your house. So usually when the telephone lines that come to your house, you have 2 wires. If you see 2 wires, that's single phase, right? You understand? Very seldom do they send 3-phase down into the neighborhood. But somewhere the single phase comes from what? 3-phase. So 3-phase feeds all the substations. 3-phase motors, 3-phase induction motors, 3-phase power supplies, and 3-phase motor drives. So all these guys use 3-phase, mainly for power distribution. This is showing you how these things work. So what we got is we got coils inside our generator, and those coils are actually separated by 120 degrees around that circle. So when that magnet spins around there, it actually generates 3 different phases. You can't see the green one. Can y'all see the green? That's hard to see, sorry. It's right here. And they're literally what? 120 electric degrees apart. So this is 3-phase. Normally they call them A, B, and C. Now what advantage does 3-phase have over single phase? Well, what happens is you get the power is distributed across 3 wires instead of across 1 wire. So that means if you measure the voltage and current in one conductor and you multiplied it, you're getting more power than you're getting out of that one conductor. So the power, instead of being on 2 conductors, is actually spread across 3 conductors. So we can send more power with less current. And we sacrifice 1 conductor and it's a lot more efficient. So these are typical high tension or high power lines. And you can see the 3 phases. So here's one right here, here's one right here, and then they're running the second one down here. I'm sorry, here they are down here. So anytime you see what they call high tension lines, you're going to see how many wires up there. You're going to see 3. That's 3-phase. Now, a lot of times they group these right here because what they're trying to do is they're trying to send a lot of current, and wire has resistance. And it's been a technique for a long, long time. If we're trying to reduce the gauge of the wire, instead of sending it on one big gauge wire, one big size wire, we split it across multiple small wires. Does that make sense? And this is what they're doing. Some of these power lines, the wires would have to be that big. They couldn't even spool that stuff up if it's stranded wire. But if they split it across 3, they would drop down to this size right here, right? But the overall gauge of all 3 wires would be exactly the same. Plus, if one of those wire breaks, you could reduce the power, but you could still get power through the system. If you did this on 1 wire, then if you lost 1 phase, you would no longer have 3-phase, you would have single phase. So there's no such thing as 2-phase, by the way, over here. You either have 3-phase or you have single phase. So what happens, this is, y'all ever seen this guy right here? I can bring y'all a copy of this. This is what they call the electronic formula wheel, which basically gives you, if you want to solve for R, you'd look over here, right? And there's your R formulas. If you wanted to solve for I, these are all relative to power, by the way. Then this right here would be, you'd use these. If you wanted to solve for E, this right here, Ohm's law would say what? I square R Or if we're using power, we could solve for it that way. If we're using power, we could solve for it this way. No, that makes sense. Now this is single phase. So power in a single phase system, when current flows through the resistance of a conductor, the current produces a voltage drop. Everybody understand that? There's really no such thing as a conductor that we know. We do have what they call superconductors. About the only people that uses superconductors, only commercially known, it's not even commercial. I know the Navy has some ship that uses superconductors. And the problem is that these conductors have to be put down to, I think they use liquid nitrogen to bring the temperature of the conductors down so low. What determines the resistance of a conductor? Anybody know? The material, let's say. Close. We'll put that last. Of course, the size, and then the length, and then the fourth thing is the temperature. All metals, their resistance goes up when they're heated. And we use that. We have a device called an RDT, which is a resistor temperature device, which is nothing but a big old long piece of wire, and it changes its resistance for temperature. As temperature goes up, its resistance goes up, and temperature down, it goes. It's a really good, accurate gauge. The only problem with the RDT has is just real slow to respond. It takes a little while to heat metals up and cool them down, right? So, and it varies with temperature. So if temperature goes down, the resistance goes down. If temperature goes up, the resistance goes up. So literally, if I could drop something down to absolute zero, a wire would have no resistance at all. So that means I could sell 10,000 amps on a 22 gauge wire. But unfortunately, we don't have that, right? You understand that? So every wire has resistance. If you push current through resistance, we get a voltage drop. In electrician or power, they call it line loss. That's how much voltage you lose in the wire itself. And what determines that? Well, it determines the material you make the wire out of, right? You understand? The size of the wire. So the bigger the size of the wire, the more amps it can carry. We call the ampacity. And then, of course, the length. But you look at American wire gauge, resistance is measured in 1,000 feet. So I think I can show y'all that. But that's at a constant temperature. So the American wire gauge is given at a certain temperature. Usually, I think it's 25 degrees centigrade, which would be about 72 degrees Fahrenheit. Now, Alabama Power is trying to send a bunch of power. The higher the voltage pushing the current, the less current is required to provide the power. And that's what people don't understand. Because we get into Ohm's law, and Ohm's law says, well, if the voltage goes up, the current goes up. If the voltage goes down, the current goes down. We're not talking about the load. We're talking about the source, right? You understand? What's required for the source to deliver that power? So if I've got this formula, power is equal to V times I, and what am I trying to give you? What am I trying to sell you? Power. So I would be equal to P over V. So the higher I make this voltage to deliver that power, the less current's required to provide that power. Y'all understand that concept? So what do we do when we transmit power? They do what? They step the voltage what? Step it way up. Then they transmit it, and then to use it, they start stepping it down, right? You understand? So what advantage does high voltage have? Less current to produce that power. What advantage does low voltage have? It's safer. That's exactly right. So all your high wattage devices, I'm not talking about high voltage, all your high wattage devices are designed to run on 240 volts. Are they more efficient? No, you're not paying for voltage, you're paying for what? Power. So 1800 watts is 1800 watts. If I give you 1800 watts at 120 volts, it's going to take more current than get 1800 watts at 240 volts, right? You understand that? So what's nice about that is that the high voltage, we can use basically smaller gauge wire to run it to it. So high voltage is cheaper to install, but it's not cheaper to use, right? You understand? Because you're not paying for voltage, you're paying for what? Power. All your devices that are low voltage, 120 volts, these are the devices that you want to make safe, right? So where's all your 240 devices at? They're either hardwired, your dryer. Where's the plug for your dryer at? Where's the plug at? Where's the plug at for your? It's not supposed to be. Where's the plug for your dryer at? It's 240. It's down on the baseboard. So how you have to get to that plug? You got to pull the dryer out, right? You understand? Where's the dryer for your stove at? Down on the baseboard, right? You understand? So your 240 plugs are hard to get to. So if it's 240, where's the plug for your refrigerator? It's probably behind your refrigerator. Your refrigerator runs on 120 volts, right? Where's the plug for your water heater? You got an electric water heater. It don't have a plug. It might have a disconnect, but it don't have a plug. So that's hardwired. If you got a totally electric or even a combination unit, air conditioning, HVAC system, it's hardwired. It's got a disconnect out there. That's required. So if they go out there and work on it, they can pull the power on it, but they don't have a switch on it. So Alabama Power steps that stuff up over. It depends on how far it can go. They got different voltage levels they use for what they call intrastate, interstate, and all different types of things. What type of voltage they use of over 700,000 volts, 725,000 volts. I could send 725,000 watts of power with 1 amp of current. And we got power companies generating gigawatts worth of power, right?
For example, like, one end that's power, then on our we add something to our plug, we add like 340 watts and all that, then why the breaker system? Like the metal, the breaker is 15.
I don't know what you mean. Yeah, but it's 15 amps. It's 15 amps. So 15 amps at 120 volts times 15 amps. How much power? 15 amps. How much power could that circuit breaker handle? So that'd be power the circuit breaker could handle would be 120 volts times 15 amps. How much power could that circuit breaker handle? Do the math. You can handle 1800 watts of power. So as long as you add another light, you flip on a light, that light's a 100-watt light bulb, right? You understand? How many 100-watt light bulbs could you run? Understand? So it's 1800 watts of power that's available pass through that breaker. Now the breaker don't see watts, the breaker sees amps, because the breaker don't drop any voltage. So it don't see watts, right? You understand? Breakers are not supposed to get hot. If you got a breaker that's getting hot, what does that mean? That means it's dropping voltage and you need to do what? You need to replace it. And it will trip at a lot lower current too. So breakers don't get hot. Wall outlets don't get hot because they don't produce power. That's a device. It's not a load. It's a device, and it's not supposed to produce power. It's not supposed to drop a voltage. So it conducts a current, but it don't do what? It don't drop a voltage. So if we got something that conducts a current and drops a voltage, how much power does it use? None. That answer your question? which is so dang neat, and people don't understand that. You say, okay, I turn a 100-watt light bulb on at my house. How much does Alabama Power have to give me? What do they have to give you? They give you 100 watts. That's the beautiful thing. It's just they give you that 100 watts at a real high voltage, right? You understand? It's not exactly, but transformers are over 96% efficient. So that means we only have like a 4% loss in the transformer. So yeah, they have to give you a little more. In an ideal world, 100 watts, 100 watts. When actually it might be 100 watts and 115 watts, right? You understand? That they have to provide you. And so, man, they step that voltage up. But the problem is that that voltage is referenced to earth ground, and it is looking for earth ground. So these big old high tension lines, these 250,000, 750, where are they at? Man, they're way up in the sky, right? You understand? And they're separated apart. So to even get that down to ground, we got to start lowering that voltage. So we keep lowering it and lowering it the closer it's closer to get to your house. The feed for your transformers between 1,000 volts or 2,200 volts, which is still pretty dang dangerous, right? But you look at those wires up there, they're little old tiny things. Handling all that power. Why? Because it's such high voltage, right? You understand that? And then it comes into your house, and then that transformer steps it down to the 240 and 120 that we use in our house. And the wires down drop from our house is bigger than the wires up there providing the power. Why? Because the wires providing the power is at a lot higher voltage. Does that make sense? And that's the advantage of AC. What can we do with AC that we can't do with DC? Easily. We can do what? We can step it up with transformers and do what? Step it up for use. Step it up for use. Step it down for safety. And sometimes we have to do the opposite. We don't have 440 in this building. The only thing we got in this building is 220. That robot right there is a 440 transformer, this ABB robot. And the big FANUC over there runs off 440. So what did we have to do to get 440? We have a step-up transformer. You can't see the one for the big FANUC. It's in a mechanical room upstairs. But the one for the ABB is on the floor over there. It's a 15 kiloVA transformer. So the ABB might use 15 amps, but we're having to provide it 30 amps on the locals on the 240 side, right? You understand? So if we step it up, so that's something you've got to remember. 100 watts of power at different voltages. And this is what we're talking about. So y'all see that? Voltage and resistance, voltage and current. So look, as the voltage goes, and this is 100 watts of power. So as I keep raising my voltage, the amount of work. Now you got to understand, you say, well, I'm going to go home and wire all my outlets for 240 volts. Loads are designed around a certain current. So your vacuum cleaner and those light bulbs are designed around 120 or 115 volts. If you put 115 volt across 240 volts, it's going to blow just like that. If you put your 120 volt vacuum cleaner across a 240 volt, it's going to smoke. If you put something divided around 240 around 120, it's not going to work at all. Okay, y'all understand that? So loads are designed to work around a high voltage. So that means your HVA system and your electric stove and you got electric water heater, those are designed for 240. This is three-phase. So you'll see three-phase right off the bat. All your substations are three-phase. These are three-phase transformers. A lot of times Alabama Power, what they'll do is they'll use 3 single-phase transformers and they wire them for three-phase. Now this is more efficient. This is cheaper to install. I mean, it's more expensive to install, but it's cheaper to maintain. Because if this three-phase transformer, if one of these windings goes out, you have to buy another three-phase transformer. If this transformer right here goes out, you replace that transformer. Plus, there's an arrangement called Delta. And Delta's really neat in that it will run off 2 transformers. the other two transformers have to pick up a load, but they can still run their system. They just reduce the load. It's called open delta. So that's really, really neat. So you can get an open delta with two transformers. And this is a typical power distribution system. This is out of my book, by the way, a book that I wrote, talking about AC and DC. And then this is what we're looking at. So the power company is generating 2,300 volts, and we're trying to, and over here we're getting 220 and 240. And what I've got is I'm doing a 1,000 watt load at 120 volts. How much current would it take over here? It would take 8.3 amps running through these conductors right here. The resistance of these conductors would determine how much voltage that drops, right? You understand? So what do they do on the down drop from your house? It's at least a 4-aught wire. I mean, it's a pretty good sized wire. It's almost half inch, right? You understand? Huh? Now up here, here's the transformer. Over here is 2,300 volts. So now I'm doing 1,000 watts, but it's at what? 435 milliamps. Then this is my substation, and I'm transmitting at 275,000 volts. So what's the current now? Well, the current over here is only 3.3 milliamps to transmit 1,000 watts. And then over here, we come over here, and the power company is providing me 434 amps or 435 milliamps to give me 8.3 amps, right? You understand that? Which is pretty neat. So that's what AC is. That's the advantage of AC right there. The major advantage is we can step it up for what? Transmission. Instead of using copper wire, we can use what over here? What's these transmission lines? They're not copper. What are they? Anybody know? They're aluminum. Now what advantage does aluminum have over copper? It's cheaper and it's lighter. So that means not only does it save them money on the wires, it saves them the money on these dang towers that have to do what? Support the wire. But when we get down in here, these are using copper right in here. They don't look like they're copper because, you know, copper turns green when it oxidizes. So that's why it looks green up there, but it's usually copper down on the distribution side. So these are the formulas for three phase. They're the same formulas, but we multiply all of them by the watt. Square root of 3. So what we do by using that second wire, we can send 1.73 more watts of power using 3 conductors. So these are three-phase formulas. So what we would do is if we measured the voltage in one of the phases and we measured the current in one of the phases, we would multiply those two together and then the square root of 3. That would tell me the total power being generated. D times I times square root of 3. 1.73, what happens to be the square root of 3, which is a sine wave. They're all set by what? 120 electrical degrees. The sine of 120 electrical degrees is 1.73, which is the square root of 3. But the square root of 3 is so much easier to remember than 1.73. Ain't that neat? So now you know where the 1.73 came from. Because they're all set by what? 120 degrees. By the way, over here, notice I changed R over to what? Ohms. So this is true. This is truly Ohm's law right here. And if you take AC, you'll learn why. So people that said AC, what's the two oppositions we have in an AC circuit? So in DC circuits, we got one opposition. We got ohm. We got resistance. For the people that has AC, what's the other opposition we have in an AC circuit? Y'all don't know. Who don't know AC? Huh? You hadn't had AC? Brandon, you had AC. What's the two oppositions we've had in an AC circuit? Inductance is something. The opposition, we call it reactance. So we have two types of opposition in an AC circuit. We got inductance and we got reactance. What do you need, Jay? And we both represent them with ohms. So when you get into AC, it's going to be interesting because you got to pick up another type of opposition. So this is truly Ohm's law. This is Ohm's law right here. It's not over R, it's over ohms. So that's what Ohm's law is. So it's actually V is equal to I times opposition. And all opposition is in ohms. So that's just nice to know that. And I just wanted to tell you that why I changed the R over to ohms. This is effective voltage. We already talked about that. Is everybody okay here? The instantaneous voltage of an AC sine wave is constantly changing. The DC average of a complete cycle is what? 0. And we proved that with the meter. And this gets people hurt. They'll have their meter on DC and they'll put it in an AC circuit in there and they don't think there's voltage there because it's going to measure what? 0. Yeah. The method of finding the effective voltage is take the square root of the mean of an infinite, a very large number of equally spaced instantaneous voltages along the sine wave, and then we square it. Of course, for AC, or a sine wave, that is always VP times 0.707, which is pretty neat, right? Are you okay? And it's called the effective voltage because we get exactly the same heating effect. So in a resistor, now in AC you're going to learn some neat stuff. To me it's neat. Some of y'all say, man, it's ridiculous. We have some components that have a function in the circuit, but they don't produce power. It's pretty neat. So in a resistive circuit, 120, using the same resistor, 120 volts AC would do exactly the same work as 120 volts DC. And that's why we refer to it as an effective voltage and not an average. Even though some people, you know it. So even if you get out there and they call it an average, you know what they're talking about. But it is not an average, right? You understand that? We did this, then we did that, we did that. There are 3 types of opposition to the flow of current in electrical and electronic circuits. We have resistance, and what's resistance? Opposition that does not change with frequency. And then we got reactance, which is what? So guys, when you get into AC, you'll find out that we've got an opposition that varies with what? Frequency. So we can make devices that are frequency dependent. Anybody seen one of those devices? It's a lot more. Huh? TV is anything that receives RF would be frequency dependent. We got all this radio frequencies flying around here, and they're all running at different frequencies. And yet I have the ability to grab one of them and sort it out. Ain't that neat? These are called filters, and hopefully in AC you get to that. Impedance is a term that we use for total opposition in an AC circuit. But what you're going to find out is impedance sounds so cool that just about everybody uses impedance when they're talking about AC, even if there's no reactance in the circuit at all. That's just a term. Doesn't it sound cool? In AC, you'll learn all the formulas. But we need to learn a little bit about this, not very much, guys. Opposition to current flow that does not change with frequency. All opposition in a DC resistance circuit it doesn't have a frequency component, is resistance. Reactance, and we don't need to get this. There is some little things we need to do. We have things called capacitors and we have things called inductors. And why we have to do that is that these devices have multi-functions. In DC circuits, we use these as what we call filters. What is a filter? What's that? filters out what you don't want to get through it, right? So when power supplies, we're going from AC, which is a varying garbage, over to something that's got to be steady. Well, we're going to have to filter this stuff out. So we use filters. And they're either going to be inductive filters or they're going to be capacitive. But these are going to work in a DC circuit. So when we get into power supplies, we're going to look at primarily capacitive filters. And that's going to take a chopped up AC waveform and convert it into a DC form. The first one we're going to look, the first power supplies we're going to look at are what we call unfiltered power supplies. And we'll see exactly what we get out of these things we call rectifiers. And then what we're going to do is we're going to slap a capacitor on there, and you can see now we have DC. So rectifiers produce a type of DC we call pulsating DC. We'll see that. We can see it now because we got these oscilloscopes, which is really, really neat. So capacitors do a lot of neat stuff. And here's the formulas, but you don't need to know the formulas here. All you got to know is some general rules. So in a DC circuit, what does it say? In a DC circuit, it says a capacitor acts like a really small what? Battery that can store a charge for a brief period of time. In fact, there's a type of memory called DRAM, Dynamic Random Access Read-Write Memory. This is the memory in this computer. And it's nothing but thousands of little capacitors. They either charge them up or they discharge them. They charge them up, that would be storing a water. They discharge it, it would be storing a water. Zero. Now the problem is it only stores it for a brief amount of time. So that's why it's called dynamic. They have a special circuit in the computer that goes back and constantly does what they call a refresh. But it's real cheap. So what we're going to do with this capacitor is we're going to let the DC, the AC signal, charge it up. And then when we take it away, what the capacitor going to do? It's going to have you go through the running load for a short amount of time, right? Which is real neat. So understanding, another thing that we need to understand, let's see if I got it in here or not. I think it's on the next slide. No, correct. We probably don't need to know that either. Even though capacitor produces delivering to conductors. Yeah, we can make a capacitor, guys. Now go ahead and take a break. Let me make a capacitor for y'all. Even though you hold one in your hand all the time. Huh? No, you're